Alright, so what do we have over here? We need to calculate the contact forces supporting the slab. So for this thing over here, we're essentially trying to find the reaction forces at support 1, so maybe we'll call this R1, and also the contact force or reaction force of the pillar pushing up onto the slab. And this is R2 over here. These are both unknown, so you do need to do a bit of a torque analysis. Now, first of all, we'll label all of our vectors, our force vectors, and we'll proceed from there. So what are the forces that are acting on the slab? Well, you can see this truck over here. This truck is acting down with its weight, and we know that the mass of the truck over here is 50 tons. So remember, let's convert this into kilograms. That is 50,000 kilograms multiplied by g for the acceleration of gravity. We also have the mass of the slab, and this one over here is a greater magnitude. Just draw a straight line in that. There we go. And this one over here is 300 tons, so 300,000 kilograms multiplied by g, and that is its weight force. And where is this acting? It's going to be acting on the center of mass. So this one over here, let's label where it is. So it's going to be halfway across this 13.5 meter length, and halfway of 13.5 is going to be a length of 6.75 meters. Okay, and from here we've labeled all of the forces. It's just a matter of calculation right now. So first of all, let's do the sum of all torques. And where do we want to do this? It can either be around 0.1 or 0.2. It doesn't really matter. The reason why it doesn't really matter between the two is because you're going to cancel one of the variables out. If you do some torques around 1, then that means reaction force 1 can be disregarded in your first equation. If you do some torques around 2, then reaction 2 is disregarded. But we'll just do a 0.1. Okay, this one over here. Now, we should be visualizing how these forces are going to act as torques around the 0.1. So are they going to go clockwise? It's a different color there. They're going to go clockwise or they're going to go anti-clockwise? Well, we should also be drawing an axis. So first of all, let us just confirm that up is positive, going to the right is positive, and if we're rotating anti-clockwise, it's positive. So let's look at the first one over here. The first force of 50,000 G, this one you can visualize is going clockwise around this point over here. So this means we're going to have a negative force, sorry, not negative force, a negative torque. Negative the distance, so the distance over here is 4.5 meters away from the 0.1. So we have 4.5 multiplied by 50,000 G. Okay, we also have the weight of the concrete slab. And this one over here, you can see this is also moving clockwise, so this means this is also negative. The distance from 0.1 to the center of mass we established before was 6.75, and the force over here is 300,000 G. So the torque is simply the distance multiplied by the force at that point. And lastly, the last force that's present is reaction force 2, and this is going anti-clockwise since it's going up and on the right of the pivot point. So if it's going anti-clockwise, we're going to add this force and say that we have a distance of 13.5 from 0.1 to 0.2. So this means this is our R value, our perpendicular distance, and the force acting at that point is R2. Okay, and we know all of this is equal to 0 when you sum all of this up. Now if all of this is equal to 0 and R2 is your only unknown, and we also know that G is equal to 9.8. So we are actually ready to solve. R2 is going to equal to some value. Now I'll just whip up the CAS for this. Or any kind of calculator is fine. So first of all, we can say that we're going to add everything on the right hand side. So this is just matter of algebra. I assume that this isn't too bad for most of you watching this video. 4.5 multiplied by 50,000 times 9.8, because that is the value of G. We're adding 6.75 multiplied by 300,000 times 9.8, and all of this is divided by 13.5 because we've taken both of these forces. So I'm talking about this one over here and this one. They both go to the right hand side, and you want to divide by the 13.5 over here afterwards. So that's where these numbers come from. Entering all of that, okay, maybe we'll get an approximate answer here. Seems like we get about 1.63 million. So actually, you know what? Let's do the approximate answer over here. Actually, it doesn't really matter. We've done physics. Math isn't too important at this stage. Okay, so about 1.6 million, and the frees are recurring. Okay, so that's the force of reaction 2. I'm just gonna box this up because we are going to need this value very soon, because we also need to know the contact force R1 over here. And if you want R1, you're going to need more information, and you can get this information by summing up all of the forces in the vertical direction. So if we do this, we can say, well, we know that R1 and R2 are going up, so these are both positive. And what's going down? What's going down is the negative 50,000 and the 300,000 G. So let's continue. So minus 50,000 G and subtract 300,000 G as well. All of this should equal to 0 since we don't have a net acceleration in the vertical direction. And if this is the case, then R1 is simply, well, 350,000 G. Chucking all of those numbers to the other side. And we want to subtract R2 as well to make R1 by itself. We know R2 from the previous part is really just 1.6 million. So let's just chuck all of that into the calculator again. So we get 350,000 multiplied by 9.8 subtracted by about 1.6 million. So just give decimal places just for a little bit more precision. And over here seems like we get $1.79 million. Okay. 1,796,66. Pretty sure this decimal keeps going. Okay. So if you want one decimal place, let me just do the 0.7 over here. And this is in newtons. Okay. And these are two answers over here. So R1, we need to quit the unit. So R1 is equal to this, and R2 was equal to the 1.6 million that we had right at the top. That's about it.